Internet of Things, or IoT, devices, including sensors, actuators, hardware, are only one layer of a complex ecosystem which represents the IoT value chain. They depend on the connectivity network, back-end systems, servers in the cloud, or on-site collecting and analyzing data, software platforms, billing and customer support, and system integrators. The supporting digital infrastructure is increasingly designated as part of critical national infrastructure, CNI, transforming some of the IoT and AI security vulnerabilities into infrastructure vulnerabilities. The increasing deployment of IoT shows no sign of slowing and is combined with 5G delivery, edge computing to allow for real-time processing, data analytics, and AI. Increases in IoT numbers represents a significant risk for CNI, therefore creating increasing challenges for industry and policymakers, some of which are already being addressed. P-Swarms. P-Swarms investigates the existing cybersecurity processes implemented in the water utility sector, a part of the UK's critical national infrastructure. Through close collaboration with Yorkshire Water and Nexor, they produced a new, sector-wide abstracted model representing the arrangement of cyber-physical assets, the role of the IoT, and the flow of data relevant to security processes. This model was validated through interactions with other water companies and stakeholders. After site tours, workshops, literature reviews, and interviews to establish the foundational domain understanding for modelling, the project developed an AI-driven situational awareness tool capable of leveraging external and internal threat intelligence and assisting with cyber incident response. The project also developed an AI-based randomized target defense approach which could reduce the risk of severe consequences from cyber attacks aimed at the IoT assets. The project is now exploring the compatibility of these security tools for other sectors of critical national infrastructure. Trusted. The Trusted project addresses how to enable in situ and trustworthy cybersecurity provisioning for the IoT and other similarly resource-constrained environments, e.g. industrial control systems, connecting at the edge of the internet. The ever-increasing digitalization and diversity of such constrained ICT deployments comes with an ever-increasing list of cyber threats and targeted cyber attacks that compromise their operation and can go undetected for prolonged periods of time. A fast, inexpensive and secure way to inspect traffic coming in and out is therefore needed, involving processing individual packets and looking for cyber attack patterns on resource-constrained devices. At the same time, doing so in a trustworthy manner, offering assurances that such a system will operate as intended and will not introduce itself any vulnerabilities, despite the additional functionality and associated complexity, is paramount. Processing in the same location allows remedial actions to be taken with low latency during intermittent connectivity for deployments in remote and disconnected environments, while also preserving privacy, since data doesn't have to be processed off-site. The two fundamental breakthroughs that are required to achieve this are: 1. The ability to enable high-speed and customizable cybersecurity functionality as part of the network stack processing on resource-constrained devices, in absence of any bespoke hardware acceleration or driver offloading support, such as those typically found in a data center. In Trusted, we have developed a service function chaining framework consisting of heterogeneous, kernel-accelerated and user-space software modules for efficient in-network processing on inexpensive hardware, like Raspberry Pi. And 2. The ability to authenticate devices in an inexpensive way without having to rely on always-on connectivity to external trusted authorities. In Trusted, we have used resonant tunneling diodes to create a quantum physical unclonable function circuit for strong device attestation. Using the above mechanisms, Trusted goes beyond by-design security aiming to offer an affordable solution used to easily retrofit secure, software-defined and attestable packet processing into both new and existing IoT deployments. GraphSec. The proliferation of low-cost IoT across infrastructure in a wide range of sectors has meant that many current IoT wireless transmissions are vulnerable to eavesdropping. Authentication verifies the user's identity and prevents malicious users from accessing the network. Encrypted wireless transmission protects data integrity and confidentiality. Although efficient, conventional public key cryptography schemes can be computationally unsuitable for limited IoT devices and potentially disadvantaged against eavesdroppers or attackers with significantly more computational power. GraphSec has developed new communication security methods, exploiting the physical information from grid-based infrastructure, such as water, gas, or electricity networks, to generate decentralized and robust cipher keys. By not requiring digital key exchange, it reduces the reliance on digital attributes for security, offering widespread application for IoT systems in infrastructure monitoring. Working with wireless network deployment company Real Wireless and National Infrastructure Operators Group British Water, the project ensures their innovation translates to real-world impact and influences best practice. Explore our expansive knowledge base of cutting-edge socio-technical IoT cybersecurity research findings and over 470 research publications on the PETRAS website, petras-iot.org.